All right, 10.3. We've talked about hypothesis testing. We've done a hypothesis test for one sample on the population proportion, and now we're going to do a one sample hypothesis test for a population mean. So again, remember this will be the mean, or what we sometimes call the average, as opposed to the proportion, which we did in 10.2. And looking at the notation again, we have the symbol for population mean. This is this mu naught is the number in the null hypothesis. So that is the number that we're comparing it to, and this will be the number in the claim as well. So H naught is that mu, the population mean, is equal to whatever this number is. So this number here will be whatever is in the claim. N is the sample size. X bar is the sample mean, the mean that you get from your sample. And S is the sample standard deviation. The requirements to perform the test: the sample has to be obtained by simple random sampling, or the data has to come from a randomized experiment. The population is normally distributed, or the sample size is large, and remember that the threshold for considering it large enough is 30, so it has to be greater than or equal to 30, or it has to say that it's normally distributed. There need to be no outliers. The sample values are independent of each other, and the sample size is no more than 5% of the population size. So the sample is small relative to the population. And a couple of these things may not be stated explicitly in the problem. You just need to kind of understand that they're true, because we can't do the test without it. And so they may ask you about that in the homework questions, but on the ones in the examples here in the notes, we'll just assume that it meets these requirements. The critical values come from a t-chart, which we fortunately don't have to use. And we don't have to worry about degrees of freedom, because that is necessary if you're using the chart. We're going to use the calculator, and the calculator performs this test for us without our having to use the table or anything. We're still going to find the test statistic just because the calculator gives it to us and when it runs the test, so we might as well write it down in case we ever needed to do the test the other way. We're still going to do the p-value method for the test, and those will come from the calculator. And the test that we're going to be using here, you go to stat and then tests, and then it is number 2, a t-test. So this is not from the z-distribution. This is from another symmetric distribution that is called the t-distribution, or the student's t-distribution. All right, let's look at an example here. According to the American Community Survey, the mean travel time to work in Collin County in 2013 was 27.5 minutes. The Department of Transportation reprogrammed all the traffic lights in Collin County in an attempt to reduce travel time. To determine if there is evidence that travel time has decreased as a result of the reprogramming, the Department of Transportation obtains a random sample of 2,500 commuters, records their travel time to work, and finds a sample mean of 27.2 minutes with a standard deviation of 8.5 minutes. Does this result suggest that travel time has decreased at the alpha equals 0.05 level of significance? So this is given in the problem alpha, so we're going to write that down before anything else because it's just right there and we don't have to do anything for it. Remember, this is a test for a mean, and so we're going to be talking about mu. And remember, the null hypothesis always has an equal, and the number that we're looking at, the established value, is 27.5, and those are minutes. And we're looking at whether or not it has decreased, so we're looking to see if there's evidence that mu, the mean travel time now, is actually less than 27.5 minutes. So that's what we have so far, and remember, this is the claim. So N is our sample size, and that is 2,500. And X bar, that was the mean from the sample, and the sample mean is 27.2. The standard deviation is 8.5. and we're going to perform this on the calculator. We're not going to worry about the critical value right now, but we will write down the test statistic when we perform the test. So again, we're going to go to Stat and then over to Tests, and there it is, number 2, the t-test. And we're going to put in stats. Now in a later problem we'll put in data, meaning that we have raw data, and we'll put it into a list. But for this one we're going to use stats, so we'll leave that. Mu naught is 27.5. X bar is 27.2. The standard deviation, 8.5. N is 2500. And we're looking at a left tail because we're saying is there evidence that it's less than 27.5, so that's a left tail test. And we're going to go ahead and calculate. And we have our test statistic is a t, and we can see here it's negative 1.76. And the p-value we can see is 0.039. If we round to 3 places, if we round to 4 places, it's going to be 0.0389, and you might be asked to do 4 places in a homework question. And then we compare that to alpha. So this is alpha, this is p, this is lower than this. If you look at, compare it place by place, this is a 0, 3 is less than 5. These numbers back here don't make any difference because 3 is less than 5. So so p is low. So H naught must go, so we reject H naught, and we say there is sufficient evidence to support the claim that the mean travel time is lower or has decreased from 27.5 minutes. Now we don't say anything about now it's equal to 27.2 minutes. That was just one sample. But from that sample in the test we ran, then the conclusion is that the evidence supports the fact that the mean time has gone down. We still don't say that it's equal to just that one sample value. If we go back and want to look at the picture before we finish up down here, remember we have to kind of go back and redo the test. So we quit out of that, stat, tests, 2. We keep all the information, but we go down here and highlight draw. Oh, I think I have something. Yeah, I've got something left. Hold on. Well, it's going to draw it anyway, but I've got something left over from another problem. So we'll copy it, and then I'll get rid of all that other shading that comes from a different problem. I was working in another class. The t distribution is kind of a taller bell-shaped curve. And what we've got is this shading over here. So I'm going to get rid of this other stuff. And the next one shouldn't have all that extra. All right. So then is our final conclusion down here. Are we supporting the claim? Remember, the claim is H1, or the the alternative hypothesis. This is the claim. So are we supporting the claim? Yes. Have we found statistically significant results? Yes. That's what it means when we support the claim. When we reject H0, it means that the evidence supports H1, which is the claim. All right, let's look at another example. In 2002, the mean age of an inmate on death row was 40.7 years, according to the U.S. Department of Justice. A sociologist wonders whether the mean age of death row inmates has changed since then. She randomly selects 32 death row inmates and finds that their mean age is 38.9 with a standard deviation of 9.6. Test the sociologist's claim using alpha equals 0.05. So again, we've got a mean. Always in H0, it's got an equal. So we're saying that it is 40.7. And this is just saying that the sociologist wonders if it has changed. Changed just means not equal. It's no longer equal to 40.7. She's not saying whether it's higher or lower. She's just saying it's no longer 40.7. So alpha equals 0.05. And we have 32 for N. That's a little above 30, so it's a big enough sample. And we have X bar equals 38.9 and a standard deviation of 9.6. So we'll get the test statistic when we run the test. Again, remember this is stat, tests, 2. We're still doing stats. So our mean, 40.7. Our sample mean was 38.9. Our standard deviation, 9.6. Our N value is 32. This is a not equal, so it's that first one there. Calculate. Our T value, which is our test statistic, is negative 1.06. Our P value is 0.2970. We'll get the picture in a minute. Now we're comparing this to alpha, which is 0.05. Obviously, this is considerably larger than this, so P is not low. So we do not reject H0. And we would say there is not sufficient evidence to support the claim that the mean age of death row inmates has changed. Are we supporting the claim? No. And have we found statistically significant results? No. And so we're going to go back and get the picture, and then we will move on to the next one. So. So you can see from this the probability of getting the results we got, given that this is true, the probability is pretty high that we would get a sample with this, where the sample mean was this, even with this being true. So there's quite a bit of probability there, and it's a two-tail. So again, we draw this. And that is what that looks like. Right, the next one. Michael Sullivan, the son of the author of our textbook, decided to enroll in a reading course that allegedly increases reading speed and comprehension. Prior to enrolling in the class, Michael read 198 words per minute. The following data represents the words per minute read for different passages read after the course. Because the sample size is small, we must verify that reading speed is normally distributed and the sample does not contain any outliers. The normal probability plot and box plot for the data is given. Are the conditions for the testing hypothesis satisfied? And that is a yes. The information is over here, and so that is a yes, and we're not gonna mess with that here. If this is a plot that indicates that these are normally distributed. So was the class effective? Remember, he was trying to improve his reading speed. So if this is the value that he read, the number of words per minute he read before, then the mean is 198. And we're looking at mean is greater than 198 because that would mean he improved his speed if he was reading faster. Alpha is 0.10, and we're going to use data for this, so I'm going to make sure that my lists are cleared, and then I'm going to put these numbers into my list. So I have 206, 217, 197, 199, 210, 210, 197, 212, 227, 209. And so now when we go to perform the test, we'll tell it to, we'll choose data and we'll tell it to go to list 1. So I've got stat, test 2, and now I'm going to highlight data. And the mean is 198. It's in list 1. That's already chosen, so I can leave that. The frequency is going to be 1. This is going to be a right tail test, so I'm going to go over and highlight the greater than. And when I calculate, I get my test statistic is 3.50, and my p-value is 0.0033. And I'm going to compare that to alpha. So this is p, and alpha, remember, is 0.10. Well, p is less than 0.10. So p is low. We reject the null hypothesis, and the conclusion is there is sufficient evidence to support the claim that his reading speed increased. So are we supporting the claim? Yes. Remember, H1 is always the claim. And have we found statistically significant results? Yes. And we'll go back and do the picture on this one. And you can see the area that's shaded is so far over here we can't really see it. Remember, this curve never really touches this horizontal axis, but the calculator doesn't have that great of resolution that it can show it getting closer without touching. But the area would be way over here, and it's so far away we can't see it. So we're going to draw a picture that doesn't even show any shading. Because we can't see it on our screen. All right. The last example that we're going to work in these notes, Consumer Reports indicates that the mean acceleration time from 0 to 60 miles per hour for the Dodge Intrepid was 10.2 seconds. So to go from 0 to 60. In most tests of this type, regular unleaded gasoline is used. Suppose that 41 such tests were made using premium unleaded gasoline and the sample mean acceleration time was 9.7 seconds with a standard deviation of 2.1 seconds. Does this indicate that premium gasoline tends to reduce average acceleration time at the alpha equals 0.05 level? So there's our alpha. And remember, we're talking about mean, average, mean. Make sure you know which parameter you're testing for. And our null hypothesis has the equal. And the equal is going to be 10.2. That's the established value. And we want to know if it reduces that time. So this is going to be a less than. And our n value is 41. Our sample mean was 9.7. Our sample standard deviation is 2.1. So we're going to run that test. This time we've got stats again. Enter. So our mean is 10.2 for our mu naught, 9.7 for our x bar. Our standard deviation was 2.1. N is 41. This is a less than. So we're going to choose that left tail. We're going to calculate. And we get t is negative 1.52. The p-value we can see here is 0.0676. So this is p. Alpha equals 0.05. And you can see here that this is larger than this. It's not a lot bigger. This is why it's so important to have all of that set up beforehand, because if alpha was a different value, this might be smaller. But this is chosen beforehand. Remember, alpha is the probability of making a type 1 error, and that's made in when you design the survey or the experiment. So this is greater than that, so p is not low. So we do not reject H naught. And our conclusion is there is not sufficient evidence to support the claim that premium gasoline reduces acceleration time. So are we supporting the claim? No. And have we found statistically significant results? No. Remember, everything is looking at the status quo We have to see if the evidence supports something different than that. Otherwise, we stick with this. So we'll go back to the picture, and that will be the end of this section. So we've got here, and we'll see that in that left tail we have a fairly sizable amount of probability. And again, this one could be different if we had set a different alpha, but we don't get to change it after the fact. So we go with how we set it up. And that's part of experiment design. All right. So that's the last example in 10.3.